For what we have in this particular section within Chapter 3, okay, we're looking at matrix products and scalar multiples among the topics. And we have concerning the determinant of a matrix product. Okay, say if you have a couple of individual square matrices, A and B, and they had the same size or the same dimensions, then you're going to have that the determinant of the product of A and B is equal to the product of the determinants of A and B. And you have the commutative equivalent of this. Okay, we have the determinant of A times that of B is equal to the determinant of the product of A and B. And just as an example, okay, let's say we have a matrix A, which is a 2 by 2, and we have this to consist of -1 and 5 at the top, -3 and 7 at the bottom. And taking the value of the determinant of this particular matrix, okay, so you have -1 times 7 minus the product obtained from multiplying -3 and 5. Okay, and so we have in the follow through, okay, we got the products at -7 and -15, and -7 minus -15 translates to -7 plus 15, which comes out to 8. So the value of the determinant of matrix A is equal to 8. Now for what we have for matrix B, okay, we have 9 and 4 at the top, -2 and 3 on the bottom, and taking the products of 9 and 3, as well as -2 and 4, and taking the difference, okay, and we have for the value of the determinant of matrix B, that is going to be at 35. Now, for what we have in the case of taking the products of A and B, now the product of what we have multiplying A and B in the form of A times B, we're going to have another 2 by 2 matrix where we have the top row is going to consist of -19 and 11, and we have -41 and 9 at the bottom. And if I take the determinant of this particular product, and for what we have here, okay, we have -19 times 9 for the first product, -41 times 11 for the next product, and for the difference between the products, we have what would translate to -171, and what is going to be plus 451, and this will come out to 280. And again, just going back to our rule, okay, so the product of what we have between the determinants of A and B, you have A with 8, B with 35, and again, the determinant of the product AB comes out to 280, and 8 times 35 is 280, and 280 is equal to 280. So that all is going to balance. Now, in the case of dealing with scalar multiples of matrices, and let's say that if we have A to be a square matrix of order n, and we have C to be a scalar, then the determinant of CA is going to be where the determinant of the scalar times the matrix A is going to be equal to the scalar to the nth power, okay, times the determinant of A. All right, now looking at numerical examples, okay, say if we go back to a 2 by 2 matrix, and we'll say that we're going to have A to consist of the numbers 3, 6, 9, and 12. Now, all of these values inside will be multiples of 3, but just looking at what we have at face value. So just going with the regular determination of the determinant, okay, so you have 3 times 12 minus 9 times 6, and we have 36 minus 54, which comes out to -18. Now, if I put what I have here in scalar terms, okay, so you have like A with 3, 6, 9, 12, and again, 3, 6, 9, and 12 are all multiples of 3, and if I take out 3 and just rewriting, so I have 3 times all of 1, 2, 3, and 4, okay, and this is what I have in the matrix, so I can pull out the 3 and affect everything among all the rows and the columns, but do not pull it out and convert like if you had crossing over to the determinant stage. Okay, so we have the matrix A, you have 3 times 1, 2, 3, and 4, and again we have a 2 by 2 matrix, so we had the value of n is going to be at 2, so n is in reference to the number of rows and columns. And just looking at what we have here in the rewrite, okay, so we have what's going to be your value C is going to be at 3. That's the scalar multiple. And n, you have the number of rows and columns, which is 2. And just following through, so we have the determinant of matrix A is going to be the scalar 3 to the second power times the determinant of 1, 2, 3, 4. So you got 9 times the determinant of 1, 2, 3, and 4. And just taking the diagonal products, so you have 9 times all of 1 times 4 minus 3 times 2. And we have 4 minus 6, which is negative 2. 9 times negative 2 comes out to negative 18. Okay, notice we had the identical products in this case. Now, let's say if I have a 3 by 3 matrix where A is going to consist of multiples of 10. Okay, now if I were to take the values as they are, let's say just with one of the regular ways of finding out what the determinant of this matrix is going to be. And if you notice, you have the top row has 10, 0, and 20. And just taking the sign values of the cofactors, minors, and all that. So you have plus 10 times the minor of the first row, first column. So you have 10 times 30, 0, 0, 50. And we have in the middle, we got 0, which is negligible. And since we're interested in only the non-negligible terms, okay, we just skip over, and we have plus 20 times the minor of the first row, third column, where we have 20 times the 2 by 2 determinant, okay, where we have 0 and 30 at the top, 40 and 0 on the bottom. And for what we have here, so we have 10 times 30 times 50, or 10 times 1500, and we have plus 20 times the quantity, what will be 0 minus the product of 40 and 30 in this case. So you have 20 times negative 1200. So this is going to amount to 15,000 minus 24,000. So we have a negative 9,000. And taking what we have and putting in scalar terms. Okay, now again we have a 3 by 3 matrix. So we have that n is equal to 3. And all these numbers are multiples of 10. So taking 10 as the scalar and extracting. So we have 10 times the 3 by 3, where the inside numbers are adjusted to 102, 030, and 405. And for what we have for c to the n, again, that's going to be 10 to the third. And just taking the determinant of the adjusted 3 by 3 matrix case, I have 102, 030, 405. And so I have 10 cubed, and then I have times the quantity. So I have plus 1 times the minor of what we have for the first row, first column. So I have 3005. And I have what's going to be plus 2 times the minor of the first row, third column. So I have 0340. And so we have, so you have 10 cubed is 1,000. And we're going to have times the quantity of 1 times 3 times 5, or 1 times 15. And we have plus 2 times the quantity of 0 minus 12, or 2 times negative 12. And so we have 1,000 times 15 minus 24. And we have 1,000 times negative 9, which comes out to negative 9,000. Notice, okay, you have two different approaches, but still coming out to the same determinant value. Okay, now, in looking at determinants and the inverse of a matrix. Now, for the determinant of an invertible matrix, okay, we have a square matrix A is invertible or non-singular if and only if the determinant of A does not equal to 0. And if you have that the determinant of matrix A is 0 in value, then the square matrix A is not invertible. So if it's not invertible, it's regarded as singular. Also, we have for this following property or formula. If A is an n by n invertible matrix, then the determinant of the inverse of A is equal to the reciprocal of the determinant of matrix A. And just samples here, okay, for systems of linear equations. Okay, say if I have used the determinant of the coefficient matrix to determine whether the system of linear equations has a unique solution, and we have for this system, okay, we have x of 1 minus 3 times x of 2 is equal to 2, and we also have 2 times x of 1 plus x of 2 is equal to 1. Now for the coefficient matrix, okay, you have the first column in reference to the x of 1 terms, second column is in reference to the x of 2 terms, so we have the coefficients respectively. For x of 1, we have 1 and 2. For x of 2, we have negative 3 and 1. Now, for the value of what we have for the determinant, okay, so we're going to have 1 times 1 minus 2 times negative 3, and that's going to be 1 plus 6, which is 7, which does not equal to 0, okay? And so in this particular case, we're not going to have a unique solution. Okay, now another case here we have with a 3 equation system, okay, and we have for these, okay, so you have for the coefficient matrix, okay, so the first column I have 1, 2, and 3. Next, in reference to the x of 2 terms, I have negative 1, and negative 2. And for the x of 3 terms, I have 1, 1, and 2. And attaining the value of the determinant of the coefficient matrix, and we have for the follow through, okay, so you have plus 1 times the minor of the first row, first column, and you have minus negative 1 or plus 1 times the minor of the first row, second column, and finally I have plus 1 times the minor of the first row, third column. And in this particular case, all right, so the value of the determinant of A is going to come out to 0. And in this particular case, for that particular system of equations, you're not going to have any unique solution because the value of the determinant of the coefficient matrix A comes out to 0. Okay, now looking at classifying whether a matrix is singular or non-invertible, or non-singular, which would be invertible. If we had the matrix to be non-singular, it says to find its inverse and also to find the determinant of the inverse. Okay, so we have, first of all, okay, so we got matrix A is a 2 by 2, where we have inside the first row we have it 1 and 4, second row we have it 2 and 8. And if I take the determinant, okay, so we have with the diagonal products, have 1 times 8, and then subtracting the other diagonal product, which we had to be attained from multiplying 2 and 4, we come out to 8 minus 8, which is equal to 0. And since the value of the determinant of matrix A in this case is equal to 0, we have that this matrix is singular. So there's no inverse of this particular matrix. All right. Now, for what we have in the second case, all right, say if we have another 2 by 2 matrix, okay, so you have kind of going back to what we have with A consisting of the numbers 3, 6, 9, and 12, which we had used in the scalar example. But just going ahead and getting to the value of the determinant, regardless of whichever approach you take, okay, we had the value at negative 18. And since we have that the value of the determinant is negative 18 as opposed to 0, we have that A is non-singular. So this is going to signal that this matrix is going to have an inverse. And just kind of looking at the process here, kind of going back to the old days, finding out the inverse of a matrix. Okay, so we have the matrix A consisting of 3, 6, 9, 12. And we take alongside the set of elements, okay, we have the 2 by 2 identity set at 1, 0, 0, 1. And to put what I have here in reduced row echelon form, okay, so if I take 1/3 of the first row, so we have 1, 2, 1/3, and 0. And I have not yet touched the second row, but I am about to. Okay, if I'm going to make the first column consisting of 1 and 0, and changing the 9 to a 0, I'm going to take all the second row and deduct 9 times the first row. Okay, so we have now the top row consisting of 1, 2, 1/3, and 0. And the bottom row now becomes 0, negative 6, negative 3, and 1. And I want the second column to consist of 0 and 1. And I can change the negative 6 here if I take negative 1/6 of what is going to be the second row. Okay, so just taking what we have now, okay, so that should be R of 2. And taking negative 1/6 of this, I'm going to have 0, 1, 1/2, and negative 1/6. And now, so we've got 1, 2, 1/3, and 0, 0, 1, 1/2, negative 1/6. And converting the 2 in the second column to 0, so I'm going to be taking twice the second row elements away from the top row. And for what I'm going to have here, top row now has 1, 0. Then we have negative 2/3, 1/3. Bottom row we have 0, 1, 1/2, negative 1/6. If you notice, the left half we have in identity terms, and for the elements to the right, okay, this will make up the inverse elements. Okay, so the inverse matrix A, we're going to have negative 2/3 and 1/3 at the top row. Bottom row, we have a 1/2 and negative 1/6. And looking for the determinants of the inverse. Okay, so if I take the diagonal products, we have negative 2/3 times negative 1/6, and we have minus the product of 1/2 and 1/3. And so this will come out to 1/9 minus 1/6. Okay, so this will come out to 2/18 minus 3/18 is equal to negative 1/18. Okay, and again, another approach to finding out the value of the determinant of the inverse. Okay, so we've got, again, the value of the determinant of matrix A was at minus 18. And again, with our formula, we had the value of the determinant of the inverse of the matrix is going to be the reciprocal of the determinant of matrix A. So we have 1 over negative 18. And with this approach, we also end up at minus 1/18.